minutes is actually on that one.
All right, so let's go ahead and get started. You have your mirrors and lenses lab starting today. I've asked you to prepare so that you're not walking into that completely not knowing what's going on. Hopefully you've done that. If not, do that between the end of class and the beginning of lab. So my goal today is to finish the single slit, do the real double slit, and maybe even get to thin film interference, which is to close out our physical optics, so we can leave the remainder of the time for talking about modern physics topics. So here we go. Here's the single slit, all the same geometry. Here's the single slit. This is L to the screen. We have the center of the screen, and we can talk about our location away from the center of the screen as both an angle, theta, and a distance, y. And we can ask, well, what happens when we look at some part of the screen that's not at the center? And I've done a super mega zoomed in view of the light coming from the slit. Remember that they're basically going out parallel, basically going out at angle theta. But the slit, because it has a finite width, does have light coming from all different parts of it. And so this is going to be a much more complicated interference than the double slit where we just had two, where now we have to somehow do an interference of a bunch of different waves coming from a bunch of different parts of the slit. So they're all going out roughly parallel, but as you go from the top of the slit to the bottom of the slit, the waves will be progressively out of sync until by the time you've gotten to the bottom of the slit, you've had a chance to develop a phase difference, which I'm labeling beta, relative to the first one. So it's understood that the first wave, just for simplicity, has a phase angle of nothing, and then progressively, as you go down to the other side of the slit, you've accumulated a phase difference, beta. So we got as far as drawing the phasor diagrams of what's going on, and we're going to complete that work today. So here's what happens at the center of the screen. If we take all the waves, the little contributions that are adding up, well, they're all going to sync up perfectly, and so we get a overall amplitude which is the maximum amplitude possible, E prime max. But for any part that's not the center of the screen, so let's take a look at one where somewhere else. What's going to happen is that the first wave, if we take that to have zero phase angle, the next one is a little bit off from that, and the next one's a little off from that, until you get to the other side of the slit, where the phase angle is beta relative to the first one. So if we connect, as we usually do, the tail of the first to the head of the last, that will be our resultant, E prime. That's the amplitude observed at the screen. And this is definitely taking that phasor stuff we were talking about earlier up to the next level, because now we have essentially split all the different waves coming from different parts of the slit. It's into a continuum, okay? So we're basically chopping up the width of the slit into infinite amounts, and we're trying to figure out what is going to happen. So the more tiny little pieces I can break this up into, the better. And in the limit that I split it up into a bunch of tiny little bits, this is going to form an arc length, okay? So basically what I have to do is a little bit of geometry here to figure out what the heck is going to happen. I'll do that geometry over here. Basically, I have that this right here is what I will get if I split up the slit into a bunch of different pieces. The length of this, by the way, is just E prime max. Because if all of these little amplitudes added perfectly in a line is E prime max, now I'm just bending those, and so because they have a phase offset, it's going to form an actual amplitude that's a little smaller, E prime. So let's work out the geometry of this. This is an arc length, so I might as well go ahead, and this is when we get really weird and abstract, where the phasor picture is incredibly worthwhile, but at some point it's like, what are we doing? We're analyzing some weird geometric object, okay? So this is a situation where just doing vector addition by components is not going to work because we have this weird curved shape. So I'm going to go ahead and just draw myself the piece of the circle that this arc length has come from, and then just try to work out what's E prime. So if the very last wave makes an angle, it has a phase angle beta relative to the first, it turns out that this also sweeps out an angle beta. That's not hard to see. Okay, question?
How do we make the assumption that that's circular and instead of like exponential? It looks, like. Yeah.
Because as you move down the slit, the offset is going to be progressively. So if we decide to split this thing up into 10 equal pieces, then the offset from the first to the second piece is the same as from the second to the last one. So it is a constant curvature, which means it's a piece of the circle, right? So when we split up the slit, we wouldn't want to split it up into uneven bits. That would be weird. So let's go ahead now and figure this out. Just to make it a little less weird, I'm going to point out that E prime max is the arc length. So usually you call that S. I don't know, what do you call it in math? S? Okay. The radius of the circle, we can label that here. And what I'm going to do is I'm going to drop a perpendicular in here. That'll help me out. That perpendicular is going to subdivide E prime into halves. So this will be E prime over 2. And it's also going to subdivide the angle in half. So that'll be beta over 2. So the reason I'm doing that is because, of course, it's always easier if I can sneak a right triangle in there. It's because the right triangle is your friend, right? You know Pythagorean theorem, SOHCAHTOA, all that stuff, right? So let me look at the right triangle right here. The other one, of course, is just identical, okay? But one of them will do. So I look at that right triangle. If you want, I can sketch it out separately over here. The angle is beta over 2. This is E prime over 2, and this is the radius. Now if you're, again, what the heck are we doing? Does this have something to do with the single slit? Well, we are trying to figure out what is the amplitude of the resultant wave arriving at the screen. And we're going way abstract into phasor space in order to figure this out. So I'm going to point out that this is a right triangle. I know the opposite side and the hypotenuse. So sine's my friend. Sine of beta over 2 equals opposite over adjacent, right? So I can just solve for E prime here. E prime will be equal to 2 over, let's see, what is it? 2 times r sine of beta over 2. I think that's right. And I'm pretty much done, except for r doesn't have any real physical meaning, at least not to me, of anything having to do with the actual physical situation. So let me get rid of that. There's an arc length formula. S equals r delta theta. That's how at least I write it in physics 250. Those of you that had Adam, is that a statement that you recognize? Arc length formula?
I do recognize that.
You guys got me worried. Okay, the most classic example of this is for the whole circle. Circumference is 2 pi r. You heard of that? Okay, so the arc length here is E prime max, and the angle that it sweeps out is beta. And so that'll allow me to get rid of r in terms of things that I actually understand would physically make sense to the situation. So I plug in that r, whatever the heck that is. I'm cleaning up after myself and trying to get back to things that I understand in the original physical situation. R is E prime max over beta. And then I'm basically done, but I do want to show you a way to compactify the result so that I can write it shorter. I'm going to actually take these two guys, group them together, and I'm going to write my solution like this. That is equivalent. I've just kind of put it in an awkward way, all right? So this thing appears so much in some certain applications that it actually does get a name. Sine of x over x. This is defined as the sinc function. Okay? So that's a way to just write it more quickly if it's a function that tends to come up all the time. And the 3, if you don't know, the 3, so I didn't add an extra or the equal sign for no reason. That means defined as. Okay? So it's just equal, but that's the definition of sinc. So what do I have? I have that E prime is equal to E prime max sinc of beta over 2. So after all that, I have found a compact expression which tells me what is my E prime, what is my resulting amplitude that's going to arrive at this point in the screen, and it will be some fraction of E prime max, and that fraction is given by sinc of beta over 2. Okay? Now, of course, my ultimate goal is not to talk about the amplitude. My goal is always intensity. So remember that we learned that the actual brightness observed on the screen is proportional to the amplitude squared. So let's just cut straight to the chase here. So the I prime will be I prime max sinc squared of beta over 2. All right? Now this right here, you don't have to redo all this geometry. It's good to see it once. It's good to see the power of all the stuff you can do in phasor space, doing all these geometrical shapes. But that is available for you. And if you don't remember what a sinc is, the sinc definition is there as well. Okay? So before I even go back to the single slit situation, I want to make sure that you guys are dialed in to the properties of a sinc function. So let's just double check what's up with the sinc. Okay? Are there any questions on the derivation here before I guess I don't have to erase that, but are there any questions? Okay, so let me talk a little bit about a sinc function. In fact, let's just jump to sinc squared, because sinc squared is what we ultimately really care about. So let's pretend we're in math class, okay? So there's nothing to do with a single slit. I just want to plot x, and I'll start plotting with your good old friend sine squared. Okay? So sine squared, this should not be a shocker. Your graph, your classic sine squared function. Looks like that, right? So it's basically like a sine, except everything gets flipped up. It's not absolute value of sine, so there isn't any weird jump cuts. So the slope does go to 0 here. Is this okay? Okay. So this is 0, x, and what's the first value here where the sine squared goes to 0?
If it's pi over to pi.
Pi.
Squared.
Pi squared.
Nah. 1 squared.
Pi, okay. What's the next one I'm afraid to ask? 2 pi, thank you. Okay. So let's go ahead and take a look at sinc squared. I'll do that in a different color. So what a difference a c can make, okay? So, first of all, if you have sinc of x, that's sine of x over x. So the first thing that I will point out about this is that if the numerator goes to 0, the whole thing will be 0. So generally speaking, it has the same zeros as the sine function, right? So if I were to sketch this, it would not be weird to put zeros there, okay? The only one that has a little bit of an exception is if you put in x equals 0. If you put in x equals 0, well, sine of 0 is 0, but you get a 0 in the denominator as well. So you get 0 over 0. Is that 0? No, that's undefined, so you use your favorite mathematical technique to figure out what it actually is. What is that called?
L'Hopital.
L'Hopital's rule. So if you're wondering if that has any use anywhere in physics, this is an occasion where it does, okay? So you take the derivative of the numerator, take the derivative of the denominator, you take the ratio again, this is L'Hopital's rule, and you find that it's actually not 0, it's 1. Okay? And the other thing, of course, is that the amplitude, unlike a sine function, as you go to larger and larger x, you're dividing, so it's going to fall off, right? It's going to have an envelope. So it actually looks something like this. So that's a sinc squared function.
That's dope.
You can even draw this envelope. This envelope that is talking about how this gets reduced goes as 1 over x. Now, one of the complications of this envelope is that it actually does shift the maxima, okay? If you're talking about sine squared, not sinc squared, but sine squared, the black one, you know the maximum goes to at what value? 1.5 pi, right? 3 pi over 2? Well, that's not what happens with this one. So if this is just good old 3 pi over 2, the maximum of the this new function gets shifted a little bit to the left. Why is that? Well, think about it, right? If I have this, imagine this little hump here is a little sand dune, okay? And I come in and I step on it flat-footed, it's not going to change where the peak is. But if I come in and I step on it kind of diagonal like this, it's going to shift the peak over. Now, let's say you wanted to find the peak of it. Let's say you just, what do you do when you want to find the maximum in calculus? Take the derivative, set it equal to what? 0. Try that for fun and solve for x. And you'll find you can't.
Thank you.
Okay?
Thank
You
you.
can take the derivative, but you get up something that can't be solved for x. You get some convoluted thing where you can't extract x. So in fact, if you wanted to find them, you'd have to go numerically. There is no solution, okay? So we're not going to worry about the maximas for that reason. So this is impossible to find an exact solution. So that makes basically our quest for a maximum is just gone. Okay? Now, if someone held a gun to your head and asked you to estimate, yes, it's really close to 3 pi over 2. So you could say that's the best I can do if you don't give me a computer to solve for it. But our main goal here is going to be to find the minimum. Those are straightforward formulas to find. Okay? So we're going to be asking about when does this whole thing go dark? The minimum. Okay? Now, before I get too far, we've just found that this is a sinc squared function, so we've just found that the pattern should look like this somehow. So the brightness pattern on the screen should have one big central lump that is the most intense, then it goes to 0, then it makes a little bit of a comeback, but it's not as strong as before, right? So it's like when you go see a band from 20 years ago and you're like, these aren't all the original members, this is not quite as good, okay? That's what happens with these. These progressively get smaller, okay?
You're on fire today, Professor.
Yeah. So let me show you what happens with the phasors. Now I've certainly done the math here that it's a sinc squared function, but I want to just show you phasor-wise what happens. It's kind of an interesting journey. So, let's see if we can turn all of those off. So here's where I start. I've got this applet that you may recognize from earlier in the semester. This applet allows a maximum of 10 waves, so that I can only split up the light coming from the different parts of the slit into 10 pieces. And at this point, I'm at the center of the screen, so I've got 10 that all line up perfectly, and it makes a gigantic wave. And that's the maximum amplitude we're starting with. Now, you can see right here, beta is 0 pi, okay? So then, we go to something like this. That's the one that I just did the geometry for. You can see that the different waves are starting to go a little bit out of sync with each other. So it's something similar to what I've just drawn here, okay? And you can see the amplitude is reduced a little bit. Just look at the length of the total phasor. It's of course still going off the screen. The reason why is because I need to save time I need to make sure that the stuff later isn't too small. Let me show you what happens next. This is beta is 0.5 pi, half a pi. So you can see this one and this one are pi over 2 apart, okay? Then I go to this one. So this is the phase shift across the entire slit is pi, okay? So you can see that this first one and this last one are pi off. Now if I just had that for a double slit, if you had one that was 0 and one that was pi, that's already destructive. But we don't have that yet, because of course you have all these other waves too. In fact, the resultant looks like this, okay? So we're still not even at the first destructive. We still haven't yet traveled from the center of the screen to the first place where the waves cancel. So let me do that. That's the first time that they kill each other. They make a circle. So of course, if the first one and the last one have an offset of 2 pi, well, the whole thing is closed into a circle. They cancel each other out. You can see the resultant, this back line. Okay, so here we are at the first destructive. Okay, question?
On the drawing, where's the first destructive is gonna happen?
So the first destructive, it's this one right here. This
Right
is
here,
where they
okay.
kill each other entirely, right? Now let's find out what happens after that. And what we have our eye on is why is it that after you hit the first destructive, you can climb up to a secondary peak before you again go to completely destructive. So let me take a look at what happens after this. So here we have that it's starting to coil around like a snake, okay? So I basically put the first turn, the first, everything that causes the first circle in blue, and then I've colored the rest in different colors. So now this is the phase offset across the whole slit is 2.5 pi. So the first 2 pi just brings you in a circle, but because now you have more after that, you do get a resultant again. But it's never going to be as big because you have to expend a lot of stuff going in the first 2 pi. So that's length, total length. Remember, the total length of this has to stay the same. So if you spent length going in a full circle, you don't have that much length left over to go back up to the original. It's like a coiling snake. It just gets smaller and smaller. Let me do one more. This is beta of 3 pi, okay? So notice here that I got 2 pi, which coiled me up to the beginning, and then of course, then from here to here I have another pi, so now my resultant's like this. It's like this little arrow that's trapped inside an ever-closing circle, right? Okay? Can't get out, okay? So that's what keeps happening. It makes these little comebacks, but essentially every time that this thing is wound into a full turn, 2 pi, 4 pi, whatever, then it cancels out again. That's the phasor representation of what's happening here, okay? Is you have a finite length and you're curling it up more and more and more. And it's eventually going to wind down to nothing, okay? Does that make sense? I know this is getting really abstract. I hope that helps rather than hurts, okay? Any questions on that before I close this up? Okay, so if that's helpful in terms of seeing why this happens, then great. So what we have seen, this beta value, as this beta value, with the exception of 0, which of course is special, when you go to 2 pi, 4 pi, 6 pi, any multiple of 2 pi, you're going to get destructive interference. So that's when the phasors basically look like this. So I guess I can draw it here. This is when it's looped around once. This is when it's curled around twice. And this is when it's curled around 3 times, so it's going to get even smaller. 1, 2, 3. And so we go over here, and of course, sine squared, well, I should say sinc squared, of beta over 2, well, what's going in there? That's pi, 2 pi, 3 pi, right? Which are the classic zeros of a sine function, right? So there's your minimums, pi, 2 pi, etc. So I didn't bring the laser back, but I did shine this for you on the wall. And hopefully you saw that this is what it looks like. It has this big central peak, and then it has these ever decreasing satellite peaks as you go out, separated by dark spots. Okay, so now let's just go ahead and finish it off and be done with it. So, of course, we go and we say things like delta L over lambda is equal to beta over 2 pi. Okay? So now we essentially bring all of our stuff that we already learned from the double slit into play, with the understanding that we're talking about the very first wave and the very last wave. Okay? So if these two have had a chance to develop a path difference, delta L. That path difference as a fraction of the wavelength will indicate what phase offset they have, right? So I solve for beta so that I can get ready to plug it into my equation. And let's just say before I do that, I'm going to plug in both of my approximations, right? So my two approximations, what's the path difference? Approximation number 1 tells me that the path difference will be W sine theta. So it used to be D sine theta, now it's W sine theta. So instead of the path difference between one slit and the other, it is the path difference that has a chance to develop across the width of the slit. And then, similarly, we said that tangent of theta equals y over L, and we approximate that the sine function is basically the same thing. Now, as I'm doing this, you may find yourself needing to just write down these same steps. Okay? So this is something where I can't ask you to go off too far off the path. I basically have to ask you to just replicate this, and this ends up being y over L. Okay? So it's basically the exact same thing we did already with the double slit. The only difference is that D is replaced by W, and of course we're using beta instead of phi for the phase angle. So let's go ahead and put all that stuff in. What we will wind up with is I prime as a function of y. So we sub in for beta, and let's make sure I get it right. This will be pi wy over L lambda. Okay? I think that's right. Okay? So there's what I have. That is a very useful equation if you want to use it on the exam or on the homework, or on the exam I should say, then you want to make sure that you can put it together from the pieces that are available on the equation sheet. That's the rules of the game. Okay? If you want to memorize that just so that you know what you should be getting, then that's up to you. Okay? So let's draw it. Basically just take this thing that I already drew and draw it properly. So, got that classic look of a sinc squared function. Like so. And as I mentioned, we've given up trying to find the maxima. It can't be done analytically, but we can find the minima. Okay? We know that in order for this quantity right here to zero out the sinc function, we've already said it has to be an integer multiple of pi, right? So if we want to find the minima, the dark spots, then the argument pi wy over L lambda has to be a whole number multiple of pi. That's just finding the zeros of your sinc squared function, which are basically the same as the zeros of the sine function. We just have to make sure we exclude 0, because that's the one place where sinc and sine are different things. So when I say m here, because sinc is not sine, we have to exclude 0, but the rest of them, we're good to go. Okay? So remember, we have to exclude 0. So if we solve this equation, we will, for y, what will we get? We get y of the destructive spots. And here's what you get. M lambda L over W. Now, if that looks reminiscently familiar, that's because if you replace the W with a D, this was something we got in the double slit, except this was the double slit constructive. Now it's the single slit destructive. That shouldn't be a huge surprise because the, let me write down for comparison, I prime of y, this is for the double slit, the argument was very similar, pi dy over L lambda, but this was a cosine squared function, not a sine sinc squared. So it's no wonder that when one has a destructive, the other one has a constructive, because sine and cosine are offset like that. Does that make sense? So let's go ahead and put it in. Remember, don't put in y equals 0, or sorry, m equals 0. That'll give you y equals 0 as a dark spot. Nope. It's the brightest spot of the whole pattern. Start with m equals 1. This will give us lambda L over W, 2 lambda L over W, so on and so forth. I can label the m values m equals plus 1, m equals plus 2, so on and so forth. That is our goal in the single slit pattern, to find the locations of the dark spots. The bright spots are approximately, though not exactly, halfway. So let's take a look at the properties of this. The central peak is where most of the action is. Not only is it the brightest, but it's also twice as wide. So if I wanted to talk about the spread of this, the width of it, it's 2 lambda L over W. The reason why is, of course, L'Hopital's rule forced us to skip one of those. So that's one of the best ways you can tell a double slit and a single slit pattern apart. One of them, obviously, is the diminishing intensity. You can tell the single slit because the center of the screen is the brightest and then the dot is going away. But sometimes, as on the homework, the diagrams aren't that good, so you kind of have to, they don't give you the nice shading of the intensity. The other way you can tell is that a double slit, we talked about the alternation of the spots to be perfect like clockwork. And so one of the questions I always get on the double slit problems on this last homework is, where's the center of the screen? It doesn't matter, because the pattern is exactly regular no matter where you can take the center of the screen anywhere you feel like it. But that's not true here. You can always tell where the center of the screen is, because not only is this the brightest, but even if the brightest is not indicated on the diagram, it's the spot that's twice as wide as all the other spots. Okay? These satellite peaks, which I'll call these secondary ones, so quote unquote satellite peaks, their width is only lambda L over W. Okay? So in these single slit patterns, the central peak is kind of like the big show in town. It's the brightest, it's twice as wide, and oftentimes it's your only interest. You don't even care about the fact that there are these small little comebacks on the fringes. You care about the central peak. Any questions on that? Okay, so let me, yeah.
So in the double slit experiment, we always make the assumption that we had ideal conditions, that intensity doesn't fade as you really go outward.
Right.
Does that mean if we don't include ideal conditions, that this will actually fade even faster because it's already declining under ideal conditions?
Well, so in this case, there is no, the ideal conditions already include the fact that the slit has finite width, which all slits do. So in a certain sense, this is more realistic. The double slit that we did so far is unrealistic in the sense that each slit is infinitely narrow, which is impossible. So the very next thing I'm going to do is go back and revisit the double slit and recognize that even in a double slit, each slit has finite width. And I'll do the real double slit. But this is very realistic already in terms of the single slit. And that's why it's so complicated, right? It's got all this sinc squared business. There's still approximations that are made, of course, right? But we've captured most of the realistic scenario here already. So it's a double slit that is kind of lagging. We'll go back and revisit that. So let's do it. Let me give you an example of where you may have already experienced this phenomenon. Let me again do it with sound, okay? So what is this going to be? You're going to have a single source, like one speaker, and then your slit is going to be an open doorway, okay? And this is a hallway, so you're going to be walking down the hall, okay? So we already talked about the fact that if you're talking about the central peak, we can talk about looking at the product of these two quantities here, taking lambda and L over W and grouping them and sort of thinking that as two quantities. We talked about the fact that the wavelength of sound is not that small, so L over W doesn't have to be some extreme value in order to get a finite spread. So for instance, you might have that the sound spreads out like this, kind of represent it like this, and I'm just going to draw that first central peak. I'm not going to bother to draw the satellite peaks. Okay. So this is what the word diffraction actually means. The word diffraction basically is a word for light for a wave bending around a corner. Okay. So the central peak that you get here can be significantly wider than the doorway itself. Okay. So diffraction is kind of a word for wave bending around a corner. Okay. Now notice though that it is wavelength dependent. So if this was a larger wavelength, all things else being equal, larger wavelength means larger central peak, and then I can draw another wave that might have a smaller wavelength. We're talking about sound here. Unfortunately, I drew them with the colors that are exactly the opposite for visible light. So the point I'm trying to make here is that this spreads out less. Okay. Now a larger wavelength, that's like bass frequencies, and a smaller wavelength is like treble. So not all the sounds bend around corners the same. The bass has an easier time bending around the corners, and you've probably had this experience walking down the hall. You hear the muffled low frequency first, and then only as you pass more or less in front of the doorway do you hear the crisp highs. Bass has an easier time bending around corners. Does that make sense? Have you had this experience with muffled sounds of indirect sound, and only when you get very close I'd have some sort of direct, more or less direct line of sight, so to speak, to the speaker? Do you hear the highs? Okay, so that's an example of this phenomenon with sound. Of course, it's always got to be more extreme with light. Because the wavelength of light is so low, you need a very, very crazy L over W ratio to get this pattern to spread out enough to see it. So I showed you last time, I shined the single slit pattern on the back wall, and my width of my slit was like a micrometer, and then the length from the slit to the screen was like many, many meters. Basically, if the wavelength of visible light is on the order of nanometers, I need this to be on the order of a million in order to dig myself out of that hole where my pattern would otherwise be too smushed to differentiate the brights from the darks. Are there any questions on that? So all this phenomenon was first observed with sound, and then light, it really requires extreme conditions to be able to see these things. The last order of business is to do the real double slit. So this is a quote-unquote real double slit, where you have basically, I guess I'll just draw the whole scenario here. It's too small to see what's going on. But if I do a mega zoomed in view, here's what I have. I have two slits separated by D, but each slit itself, of course, has finite width. And I'll give them the same width. It's very hard to cut a slit that has no width. Okay? So we have a bunch of stuff to do. We have light coming from all different parts of this slit, interfering with each other, and adding on to that, we have a bunch of light coming from all parts of this slit, and then not only is there interference across each slit, there's interference with the two slits to each other. Now you might think this is going to be a total mess, but here's the lucky part. If we are reasonable with this, here's what happens. You're going to have a single slit pattern over here like this. That's from one slit. You have one from the other slit, which is more or less exactly the same place. They're shifted off by perhaps just a little bit. And then what you have is that will inform the intensity of the double slit pattern. So this just forms the envelope, and then the double slit pattern happens inside it. And this, by the way, when I showed you the double slit, you already saw the single slit effects, right? That's why it didn't go like clockwork, the pattern from wall to wall, right? It was the entire pattern faded out after only a few degrees. That's because single slit effects killed it, right? Because even if you have a double slit, each slit itself is just a finite width. So, what do you have to do? You just multiply this times this. So for the real double slit, what's your equation? It's the double slit part times the single slit part. Like so. Question?
How do you know to multiply?
Well, you can think of both patterns as kind of going independently because of wave superposition. And then, if they're both doing their thing, if one of them says that it wants to be 0, then it squashes the whole thing. Whereas if they're both maximum, it'll be maximum. So basically, it's like lowest, like, it's like, it's basically like if they're independently working, but if one of them wants to be 0, then the whole thing has to be 0, okay?
Oh, okay.
So to give you an example, if we get this is 1, so that will be a max. But if that occurs at a y value where this is 0, where this says it's going to be minimum, well then it's going to have to be minimum, right? When you get into serious study of waves, you'll talk about this. There's things like convolution of waves and all this stuff that that I definitely can't get into. But should point out, it's not the first time we've had this. The Beats formula was like this. It was two things multiplied by each other, and the thing is, when one wants to be 0, the other one can't say no. Okay? Now, one of the things that I can point out is that our formula for the constructives that we found here was this, and the formula for destructives that we found over here was this. They're very, very similar. So, for instance, if I said something like this, if I said that the distance between the slits is 4 times the width of 1, and I put that in here, so this is 4W, what I would find is this, is that if I put in m equals 1 here, and I put in m equals 4 here, that would produce the same y value. So what I find is that the y the double slit wants to be maximum is also the y value, where the single slit wants to be 0. In which case, this one wins. So let me draw what that looks like. I'm going to actually draw it in here just for time savings. But I'm going to try to draw inside this double slit, and this right here, this first m value, you might want to label these if you're working with these together. This is m for the single slit, this is m for the double slit. So the m single slit first one is going to actually kill the fourth double slit. So I'm going to try to draw inside here. So this is m equals 0, 1, 2, 3, and okay. So that is the m double slit of the fourth one gets killed. So we have the m equals 0, m equals 1, m equals 2. This was the m equals 3. It's almost dead. This is the double slit. The fourth double slit maximum gets killed by the first single slit minimum. And I should draw it on the other side too. So this is 0, 1, 2, 3, and squash. Okay? So what do I have? I have 1, 2, 3, 4, 5, 6, 7. I have 7 brights within the first envelope. Okay? So within the single slit central peak. Okay? So you can know a heck of a lot about the geometry of the slits just by looking and seeing how many double slit maxes do you get inside the first single slit envelope, the central peak. So in this case, there's 7. There's the central one, and there's 3 to each side, making it a total of 7 total before the m equals 4 double slit is killed. Okay, so that closes us out. You should be able to do single slit and double slit problems in their entirety throughout the homework, which are definitely the hardest ones. And we'll do thin film interference and modern starting Friday.